Good evening and welcome to our TechFest Digital Festival 2021. This year we're again hosting our festival online due to the ongoing current events, which seem never ending, but I'm sure one day we'll be back in person. The feedback we received from last year's festival was so positive, and being online has opened up new possibilities for our audiences, meaning we're not restricted just to our little corner of North East Scotland. And as you can see, we've got people from further afield, which is grand. As ever, our thanks go to our joint principal sponsors, BP and Shell, and also Equinor, who are kindly sponsoring our digital programme. As this is a webinar function, all your cameras and microphones are turned off and muted. But if you do have any questions about the presentation, you can put your questions in the chat box or the Q&A box at the bottom, and we'll do them at the end. It is also being recorded this evening as well, just so you know, but that means it'll be on YouTube once we've got it edited. We'll get it up in the next couple of days, so you can watch it again if you want to. Anyway, so I think we'll just get started, and without further ado, we're delighted to welcome you all to this evening's event, which I'm sure is going to be really interesting. And I would like to introduce our speaker this evening, who is Ed Schofield, who is from the University of Aberdeen. Okay, over to you, Ed.
Hello, folks. Many thanks for joining us this evening. So we've got a presentation for you about the microscopic world linked to plants. So I'm a pollen analyst by training, and the video that you're going to be shown will talk to you about that and the science surrounding it, particularly in terms of using that technique to reconstruct vegetation in the past. So I think I'll let the video do the talking. So it lasts about 40 minutes, and then we'll have some live Q&As at the end. So I understand that we're going to get the video running now. So I'll let the organisers just set that off. Thanks.
Hello and welcome to this presentation in relation to TechFest, North East Scotland's annual science festival for 2021. My name's Dr. Ed Schofield. I am a lecturer in the Department of Geography and Environment at the University of Aberdeen. This is within the School of Geosciences. And my specialist area of expertise is using fossil pollen and spores to reconstruct the vegetation as it was in the past. So what I'm attempting to do today is to bring to you some of the science behind that process, particularly the practicalities of what would be involved in undertaking this type of research. And also to present you with an example from North East Scotland of how this type of science can be applied, and the particular case study that I have for you here is from the hill of Bennachie near Inverurie in North East Scotland, which perhaps many of you may already be aware of. You may even have gone walking there in the past. So hopefully this will be of interest. I'm attempting to pitch this at an audience age range of anybody who's 15 or above. So just before we get into the details, just another note about the research. So this is actually connected with a project under the title Voices of the Future, collaborating with children and young people to reimagine treescapes, which is a Natural Environment Research Council funded project that's going to run over the next 3 years. Basically, the project is much wider than just the work we're going to be doing in Aberdeen, but it involves looking at young people's hopes for the future in terms of creating and caring for trees and woodlands, what we might term treescapes. So obviously, these are vitally important for many reasons, not least for the sort of carbon capture and storage potential, but also for things like maintaining biodiversity, but also for aesthetic and other practical reasons. So if you're interested in what you hear from me today, there's a Twitter account at CYP Treescapes that you can choose to follow that will keep you updated, not only with my progress on the project, but with that of my colleagues, both within Aberdeen and at universities throughout the UK. So I want to begin by taking you back within the British Isles to a situation around about 6,000 years ago, towards the end of the Mesolithic, the Middle Stone Age, the point when the point prior to agriculture, when people were still followed lifestyles that involved hunting, fishing, and gathering. And at that time, the coverage of woodland across the British Isles, of what we might term wildwood or primary undisturbed woodland, was near complete. So that situation obviously was going to change very dramatically with the introduction of agriculture and later with industry, because obviously we're aware of what the landscape looks like today, where the majority of our landscapes are quite open vegetation units. So how do we understand how vegetation has changed in the past and the types of rates of change that have been going on? Well, one of the key methods for this is to actually look at the pollen grains that these plants produce and are then preserved in various things like lakes and peat bogs, and see how they contain a record of how that vegetation is changed over time. So this area of science is known as pollen analysis or palynology. So if you want a textbook definition of what palynology is, here's one for you. Pollen analysis is a technique for reconstructing former vegetation by means of the pollen grains and spores it produced. You can see a couple of pollen grains just on the right here. I'm going to show you a wider variety of these types of objects a bit later in the talk. These are actually pollen grains from the sheep's sorrel. Yeah, we'll talk a little bit more about that when we come to the process of actually looking at determining how we identify these objects. But in terms of the technique itself, it's been around a very long time now. It was introduced in 1916, so been around for over 100 years. And what the technique does that is very useful is obviously plants and plant communities respond to things like the climate and to people's impact on the environment. So it allows us to make deductions about those types of things in the past. So how landscapes have changed during prehistory and early history is a key area that the technique is used to look at. So what is pollen? Of course, it's the male reproductive part of the plant, and its goal obviously is to reach a flower where it will then obviously fertilize that plant and produce seed for reproduction. But of course, the vast majority of pollen grains that are produced by flowers don't fulfill the goal they're intended for, and they just simply end up landing on or settling on other surfaces, in which cases, if the conditions are favourable, they may then become preserved and form an archive of environmental change. So the two key methods that pollen are dispersed is just simply by the wind, or these can be carried more directly by insects. So there's some couple of terms for you here, more scientific terms for those processes of dispersal by wind: anemophily, dispersal by insects; entomophily. These are quite important a bit later down the line when we come to interpret our data, because plants that disperse their pollen by the wind tend to produce much more pollen than those that are insect dispersed. In terms of the size of these objects, we're generally talking about them being in the range 25 to 35 microns. So micron is a millionth of a meter. And so obviously these objects are microscopic. They are not visible to the naked eye, and you need to use a microscope to observe them. And we'll talk about that in a little bit more detail in a moment. So talking about preservation of pollen grains, there are two sort of sedimentary contexts, or places where sediment collects and builds up over time, that are really key for pollen analysts in terms of selecting sites for these types of studies. So pollen's best preserved in any setting that is waterlogged, meaning anaerobic, so oxygen is kept out of that environment to slow down rates of decomposition or even halt them completely, and also slightly acidic, so the pH of that environment being under 7. And the two most common settings that satisfy these requirements are lakes and peat bogs, which are obviously very wet, and particularly in terms of peat bogs, typically have these very sort of acid plant communities growing upon them. One of the key principles underpinning pollen analysis is that of stratigraphy, which is simply the arrangement and succession of sediment units as layers. So we've got an example here just of a soil pit where you can see a few, well, at least a couple of different sediment units here, a much darker peat overlain by a much lighter peat here. And this peat contains the fossil pollen grains and spores that we're interested in. Now, in terms of this being forming a record of environmental change over time, obviously it's important that this sequence remains undisturbed, because we have to be sure, for example, that fossil A, which is down at the base, which is the deepest of the three, is older than B and C when we come to look at our profile. And similarly, we have to assume that B is younger than A, but older than C, and so forth. If there's any type of mixing or disturbance of this sediment column in any way, containing this essentially window into the past, this can invalidate that deposit for palynological study, because you simply get all the microfossils of different ages mixed up together and you can't determine a sequence of change over time. One of the problems that we often face in the British Isles when we're looking for sites to recover our pollen cores from is this process of peat cutting that has gone on for many thousands of years in many places, where people essentially have stripped off the top of peat bogs to burn this material, largely for domestic fuel. You can see blocks of peat that have been cut here drying in this instance. So this is actually a photograph I took very, very recently in Shetland, where this practice still goes on today. But of course, what can happen then is if this has occurred on your peat bog in the past and you're not aware of it, and you go out and you core this area, you select a sediment core that contains the microfossils for the study, and you can find that perhaps a few thousand years of the top of your sediment core is missing. So talking about sample selection, and before we get on to sediment coring, let's just talk about different ways of collecting material for analysis. So the easiest way to do this perhaps is simply just to dig a shallow pit in the ground with a spade. Very, very basic process. Clean the faces of the section, as you can see here, and then simply insert a metal tin into that face. So what we do is tap this in with a rubber-headed mallet, and we'd recover a column of peat and take that back to the lab. But of course, what this only allows us access to the surface deposits, really. I don't know if anybody tried digging a hole that's much deeper than about 1/2 metre. It's quite difficult. So what we need to do then is we need to have ways of accessing the peat that is much deeper. So you can see a picture of myself using a piece of sampling equipment known as a Jowsey or Russian corer. What this is simply a metal chamber with a sort of cone on the end, a bullet nose, an anchor plate and a fin that we push into the ground, and we rotate this 180 degrees, we turn it, and it cuts a chamber of peat that we can then retrieve from the corer and take back to the laboratory. There are other pieces of coring equipment that are available. People may use what are called percussion-driven corers that essentially have a modified road breaker that you hammer a metal tube into the ground, or they might even use much larger scale drilling rigs to recover sediment where this is what I say more consolidated, more dense. So if it's got a lot more, say, sand, clay, or other mineral particles in there, this type of equipment is not good for that. This is really only good for soft sediments. So as you can see here, we're stood on a peat bog, and that's just the best place, the ideal place that this type of kit works. And what we have to do then is, you can see the chamber there, we have to, after we've recovered that half meter section, what we need to do then is we need to add a series of extension rods onto the top of the chamber to allow us to access the even deeper material. So you can see here I'm with my colleague at Aberdeen, Dr. Tim Myhill, doing this process of coring, adding the extension rods here. And we'll push this down and recover a sequence of half meter sediment columns. And what we do then is, you can see here's a nice peat core that's been recovered. We would drop this into a piece of guttering and wrap that up in some polythene and return it to the lab, where we'd put it in the refrigerator to stop the material decaying, and also really just to store it there ready for subsampling for the pollen analysis. So here's just a picture of a sediment core showing the process of subsampling. So what we would do in the lab is we would take regular samples at regular intervals, say 4 or 8 centimeters perhaps. And these are typically just 1 cubic centimeter in volume. So you don't need a lot of sample material to produce a pollen sample. Just cubic centimeter of sediment of peat can often contain several hundreds of thousands, perhaps even over 1 million pollen grains and spores. So we're just taking a tiny amount from each place. And if we want to go back, we can continue to take samples between these to fill in the gaps if we find that there's something really interesting happening there. So let's take you to the lab now. So the next stage then will be to chemically treat the sample to process it. So what you can see here, this is a picture of our lab with the technician at work under the fume cupboard. So we've got an extractor system on here to take out fumes from the chemicals out from the cupboard. So what essentially the procedure would involve, first of all, there'd be a treatment with sodium hydroxide, which is a very sort of a fairly weak alkali. What that would do is it would remove something called the humic acids from the sample, which are really the products of decomposition. So if you, for example, take a lump of peat, if you've ever squeezed a lump of peat and you see that brown, dark brown water running out, that is containing the products of decomposition, the liquid products of decomposition of humic acid. So that's what the sodium hydroxide does. And then we'd sieve the sample to remove any coarse debris, things like rootlets, so forth. And then we'd also treat the sample using a procedure called acidolysis, which is treatment with strong acid that actually destroys or at least reduces the amount of unwanted organic material in the sample. So the pollen grains can withstand this process because they have a really tough outer layer. The pollen grain wall is very resistant to decay, and it can withstand short treatment in quite strong acids, whereas other organic remains that are more fragile are destroyed by those processes. So the idea really here is to concentrate the pollen into a much smaller pellet, so that when we look at this under the microscope, the pollen is quite concentrated. And finally, we do a density separation, where essentially all that means is that we add the pollen sample to a chemical of a different density that allows the pollen sample itself simply to float up and rest on the top of that, and then we can sort of pipette it off into a sample vial. And that's our pollen sample there. So let's just have a look at some of these processes in a little bit more depth. So the sieving, here you can see the sieving at work. So it's a pretty simple process. We've got a very fine sieve mesh in here, and we pass the sample through that. And here you can see all the material that's caught on the surface. This is material that we don't want. This can be disposed of. Pollen grains are much smaller than the sieve mesh. They pass through and they're captured in the flask at the bottom. And then what we would do is we transfer that sample into a test tube. And at various stages in this process, then including this one, we then need to use a centrifuge to help draw off that liquid so that we can continue the processing with the different sets of chemicals. So essentially what this does, for anyone who's not aware of centrifuge, is simply you put your samples in here and close the lid, and this spins round very, very rapidly. And what it does is it rotates at 3,000 revolutions per minute. So that goes round, this arm goes around 3,000 times in a minute. And what it does is it forces all the little particles that are in the test tube, including the pollen grains, it forces them to settle down to the bottom of the tube. And then what we can do is, once the centrifuge has run its cycle over about 3 minutes, we then take the tubes out and we can pour off what is contained within that, the liquid, which we call the supernatant. So eventually we get to a stage where we've done all the treatments, we've transferred our sample into a little vial that we can see here. So you can see this is our cubic centimetre of sample is in here, and we've also added some silicon oil here, which is essentially a mountant for the pollen grains, because what we want to do then, of course, is we want to look at these under the microscope. So we put a little blob of the sample from the vial on the slide, just mix that round, put a very thin cover slip, another very fine slice of glass on top of that. And then what we do is we'd look at that down a series of objectives on the microscope that provide magnification. So in this case, you can see I'm looking at this sample using the 40 times objective. And on our microscope, we have eyepieces that provide magnification at 10 times as well. So 10 times 40 is 400 times. So what we're getting there is we're getting to see these objects at a magnification of 400 times. Here's a larger picture of that microscope. We can see our slide sitting on there from the previous picture with the objectives. Here, these rotate round, so you can have different magnifications should you wish that, which is often helpful. You see I've got my manual out here to help me with some of my IDs. I've got a click counter here to help me when I'm counting up the objects. And so I typically sit here and spend time traversing this slide, moving up and down it. Whenever I find a pollen grain, I try and identify it and I record it. So the other process here that is often typical is you come across things, you're not quite sure perhaps what they are. So we have a selection of reference material that we hold in the lab as well in this cabinet. What you can see here is a series of slides that are essentially prepared from modern flowers of plants that contain pollen, and we can look at those under the microscope and see whether they compare with what we have and make a decision on, yeah, that pollen grain looks like the other one, and we can sort of identify it in that way. So with a combination of the manual, the reference collection, you can make your identifications. So by convention, what we would do is we would count 300 to 500 pollen grains from each sample. So this may involve, counting thousands of pollen grains per core. And what we're looking for here really in terms of standardizing this is we're looking to count the pollen from the trees, shrubs, heaths and dryland herbs as a contribution to this pollen sum. We count everything else, of course, aquatic plants are included within that, but by convention, pollen analysts keep those out of this standardized sum. Here you can see, this is taking me back some way. I take a picture of one of my lab books from my PhD, and one of the things that is quite useful in many instances, especially if you're beginning with this process, is to actually start drawing some of the objects as they appear under the microscope, making little notes. And this can help if you need to go back and you're thinking this is quite a rare pollen grain. What have I found it before? What did it look like? And you can see me recording the numbers of pollen grains here. So allness, that's alder. You can see there's quite a lot of that in the sample. These 5-bar gates, each one of these means I've counted 5 pollen grains of that type. And before we look at the objects in a little bit more detail, just note that palynologists also may perform other measurements or analyses to support or complement the pollen data. I'm not going to go into a great deal of detail about these, but things that we might typically do is we might do a process called loss and ignition, where we essentially dry the peat sample, mill it to a fine powder, put it in a crucible, weigh it, then put it in a furnace at 550 degrees centigrade for 3 hours, burn off all the carbon, the organic carbon that is contained within that, reweigh the sample and work out that loss in weight that tells us basically the balance between the organic and the mineral component in that little cube of sediment. And that's quite useful often in terms of trying to judge soil erosion in the past. So in the past, for example, if you get clearance of woodland, you can accelerate soil erosion through that process, and you can often get those soils then washed into lakes and peat bogs. So it's quite a useful measure of that type of activity. And then with the radiocarbon dating, this simply means it is a way of providing ages, a chronology for our core profile. Again, I'm not going to talk about the details of that. You can, there's videos and so forth out there if you want to go and watch that. But what we might typically do is look for plant macrofossils, so fossils that are visible to the naked eye within the peat. So we've got a nice dwarf birch leaf here and some mosses on the left. These are really good for radiocarbon dating. We send them off to the lab. They measure how much radiocarbon is within those samples, and from that they make a judgment on essentially when that plant was fossilized, when it died and was fossilized, and can give us an age from that. So let's quickly have a look at some of the different types of pollen grains that you might potentially encounter. So here's a birch pollen grain. So perhaps we're familiar with this tree, with the silver bark. There's plenty of that in northeast Scotland. And what we've got here is, you can see the pollen grain wall around the outside. This is the tough resistant layer that I talked about being particularly useful in terms of the processing, so it can resist short treatment with quite strong acid, for example. And in this case, this pollen grain has got 3 what we call apertures, essentially gaps in that pollen grain wall that take on a circular appearance. We call these pores. So there's one here, there's one here, and there's one here. And these are actually, for this particular pollen grain, they take on what's called a vestibular or chambered appearance, where this pollen grain wall is separated into 2 layers, and these diverge, they separate at the pore, and they form a little chamber in this area that's quite recognisable under the microscope. You see the surface is quite smooth in this case. So apertures and the surface are quite important features for identification. So pollinologists have their own special language for a lot of these terms. You can see me pointing out some of these here. So we're talking about 3 equidistant pores. So tri, meaning 3, equidistant zono, and pores, porate. Smooth surface, the pollinologist term for that is silate. Let's have a look at another common pollen grain. From a willow tree in this case. What you can see is this has got a different aperture system. So whereas the previous pollen grain had pores, this pollen grain has got long elongated slits in the surface that we call furrows, or in pollinologist terminology, colpi. What these do is they run nearly from pole to pole on the pollen grain. There's actually a third furrow round the back here that if you were on the microscope and you were to focus down through that object, you can actually look at the back of the object using the microscope, you would see that come into focus round the back. So you can see here the surface is very much different. You've got these little pits or holes in the surface, and it takes on a sieve-like appearance, and pollinologists call this reticulate. We see our pollinologist terminology again here for the 3, tri, the zono for equidistant, and the colpate, this time representing colping. In some cases, pollen grains don't have apertures at all. This is a pollen grain from a sedge, from cotton. A good example here would be the cotton grass, this plant that we see growing on peat bogs with the cotton bud head to it. What you can see here is it takes on sort of pear-shaped appearance, and this wall, this pollen grain wall, is very thin in many places, and it's got quite a patchy surface as well. Some of it's slightly rough, but with smoother areas. This can actually be quite a fragile pollen grain, can often be found damaged within your pollen samples, and a little bit harder to identify as a consequence of that. So obviously I can't show you the complete range of pollen grains that I would typically see under the microscope, but here are just some examples. So just demonstrating the range and variety of different shapes and features that many of these pollen grains display. Again, you can see these aperture systems coming to the fore here that help us identify this. For example, this is a grass pollen grain, which is just a circular grain simply with a single pore. You can see this thing, it looks like a donut here. That's essentially the thickening of the grain wall around that pore, that opening in the pollen grain. So of course, then you've got your data, and then you have to ask yourself, well, how do I begin to interpret this? I'm not going to go into this in a lot of detail because we're getting then more into the really deeply theoretical side of things. But critical questions that the pollen analyst will need to ask themselves is, well, what is the pollen productivity of that plant? Because it does vary. So for example, of course, trees produce a lot more pollen than, say, herbs. So will be much better. So a tree will be much represented than just, say, a single herb in a pollen record. And we also need to think about this dispersal mechanism. So we talked about pollen being transported either by insects. You can see a bumblebee here. We actually, with some of the pollen, it's just attached to the insect itself and will be then carried to another flower. Or we can have the material, the pollen dispersed by the wind. So you can see some alder catkins here, essentially just hang out from the branch, and the pollen is just released into the atmosphere and blown around, and hopefully it lands on a flower. So of course, this type of method for the plant dispersing its pollen is much more open to chance than this one. So these types of plants tend to have to produce more pollen grains to ensure that some of them make it to their intended destination, where this is much more targeted, so the plant can spend less time producing pollen and perhaps invest its resources in doing other things like growing, for example. Another thing we need to think about is what we call the pollen source area. So this is essentially the size of the area of vegetation that you're reconstructing. So to put it at its most basic, the bigger your site or basin that you're looking at, the larger that area is that the pollen is coming from, that is landing on the point where you're collecting your pollen core. So let's take a really simple example. So you've got a garden pond as opposed to, say, a lake that may be, say, several kilometres across. So the small pond is just going to really allow you to reconstruct the vegetation in the area at just within a few metres or tens of metres around that space, whereas the big lake is going to allow you to produce a much wider reconstruction, what we might term a regional reconstruction. So what is happening to vegetation over maybe tens to hundreds of kilometres around that location. And one of the other things that limits us a little bit as well is the taxonomic precision of our identifications. You may notice, for example, that with the sedge pollen, we can't identify that beyond the family level. So of course there are hundreds of sedges within the British Isles. If you find a sedge pollen grain, you don't know which species that comes from. So you have to make deductions based upon the other pollen types that it's found with as to maybe whether that's a wetland or a dryland plant. So there can be some uncertainty there as well. So all these types of factors plus some other things have to be taken into account when you're thinking about the data. So let's move to the case study to show you just an example of this type of science at work. So I'm going to take you to Bennachie in northeast Scotland, obviously very close to Aberdeen. This is a picture of the tap, the highest point on the hill of Bennachie. So this is about 500 metres above sea level, and what you can see in the foreground here is this is blanket peatland. So essentially this means just a peatland that's draped or blanketed over the top of the hill. And if you go to the top of the peak and you look down, well, the first thing actually that you see is there's an old fort at the top of the hill. Some of the radiocarbon dates on this show, it was used in early medieval times. In early historic times, sorry. The area beyond that we can see a lot of forestry going on here, a lot of forestry commission, plantations, and obviously a much wider agricultural landscape. But this is useful in terms of thinking about where our pollen's coming from to land on top of the hill. So some of it will be brought up from these areas in updrafts and land on the peat surface. So here's me and Tim again, beginning our process of collecting the sediment core from the blanket peatland, so you can see the peak in the background there. And this is ultimately what we end up with. So this may look very complex at this stage, so I'll quickly talk you through this and then the features of this before we talk about the detail. So the first thing to note here is we've got our sediment column, so we've got depth, which equates to time. So these are basically ages based on our radiocarbon dates, and these are in the period AD and BC. What we've got here is, as well as we've got a summary diagram here showing the total proportion of pollen from trees, from shrubs, from heaths, and from herbs, and these various colours, and they map onto these plants as you can see them here. So I've put the common names in for all the plants as well, so that everybody can understand what these are. And the first thing to do here is to essentially look at the age of the peat column. And you can see that it goes back to around about 5000 BC, which is about 7,000 years ago. So this peat on top of Bennachie is 7,000 years old. So we're going back into the Mesolithic here, at the point where people were using stone tools and hunting, fishing and gathering. And you can see actually that the woodland for about 3,000 years is very, very stable. We've got a mixture of birch, of hazel, alder, oak, particularly in that area around the hill. You can see this column for heather here, just representing the plants growing on top of the hill on that peatland. But predominantly quite a dense woodland cover surrounding the hill over that time period, and pretty stable. And then actually things begin to move forward around about 4,000 years ago, so around about 2000 BC, we start to see things beginning to happen. We start to get the appearance, more regular appearance of herbaceous plants, things like sorrels and plantains, that if you saw them in your garden today, you typically regard them as weeds, the type of things that like open conditions, plenty of light. So this is perhaps telling us that this woodland is beginning to open up a little bit. You can see there's a bit of a decline in the woodland, particularly the birch at this time. And this is probably caused by the sort of beginnings of agriculture in this landscape. You can see the grass pollen goes up slightly from this point and stays relatively high. But really it's from this point onwards, from about 3,000 years ago at 920 BC, that we actually see rapid deforestation or clearance of the landscape around Bennachie. You can see these pollen from trees and shrubs really plummets over this about 1,000 years of time. And you can see this pollen from herbaceous plants moves in to take its place, particularly the sedges, but also these weedy plants, and also a little bit more grass as well. And you can see the declines here is particularly clear in, say, the birch and to a large extent the alder as well. And it's such that we reach a point around about the start of the first millennium AD, where a woodland cover reaches a minimum that is quite close to, in terms of what things look like today, in terms of the pollen rain. So you can see this is under 20%, perhaps as little as 15% of the pollen coming from the trees. And as I said, the trees can often be a little bit overrepresented in some case relative to some of these herbaceous pollen types. So probably got a very open landscape around Bennachie at this time, very open agricultural landscape, probably largely dominated by pastoral agriculture if you've got the grasses coming in here. So it's not really until much later, when we start to come to this period after AD 1250, that we get a further decline setting in, and we start to see things like pollen from cereal plants. So here's a pollen grain from oats, for example, at the very top, and we've got a colony sort of living on the slopes, of crofters living on the slopes around the hill. That's quite interesting actually, is that there's a little recovery you can see in the trees there over the period of the middle of the sort of first millennium AD. This is sort of the Pictish period during Scottish history, and there's a little resurgence of woodland here, and it's largely formed through the birch. So it looks like there could have been quite a bit of what we might term secondary or reconstituted birch woodland around this time. Essentially, that's landscape maybe was less intensively used than it was during this point, when there were very, very few trees. So really just quite interesting record of the vegetation history of that area over a period of 7,000 years. So I hope that's been enjoyable. Thanks for listening. And if you're in the live session, there's now a few moments for you to ask some questions.
Hi, folks. I hope you enjoyed that and that you're still with us. Hopefully you managed to get a cup of tea and some biscuits along with it to keep yourself going. But I mean, I'm happy to answer any questions anybody might have now regarding what was covered there or anything related to it. And I understand Jenny's going to monitor the chat as well. So if you want to type anything into the chat to ask, you're welcome to do that. Or if you want to actually just raise your hand and ask a question through your audio link, we're very happy to answer those questions as well.
Yeah, I'm not sure if we're getting. I know we've got one thing in the chat box. I think somebody's
All right.
saying
I'll have a quick
Mithertap
look.
isn't the highest point in Bennachie.
All right. Okay.
Oxen Craig's the highest point.
I thought it was. I think Mithertap's about just over 500, about 512 meters above sea level. I think Oxen Craig's just under 500, 490 or something like that. But I will check that. So thanks for just pointing that out, and I'll go in and check that. So that peat core that you saw me and my colleague Tim taking, so that was about equidistant from those two peaks. So for anyone not familiar with Bennachie, those are the two highest peaks on what is known sort of regionally as the Hill, which is actually a sort of a composite landscape of several peaks interspersed between moorland. So very, very nice place. If you've not visited, very nice place to go walking. And as I showed you that picture from the top, you get a fantastic view of the surrounding landscape, and it really it can help you as a somebody who does the type of work that I do. It can help you think about how that landscape has changed over time simply by visiting it and looking at how that landscape is shaped today, and then thinking about those data that I had from the pollen core and maybe where those vegetation units would have been in the past.
Yeah, I was just wondering actually, how deep have you ever gone to get a sample? I mean, I know that the graph you showed at the end was like 2 or 3 meters deep, but how deep would you normally go?
Yes, so that peat core was actually almost 5 meters in depth, and it really surprised me when I found as great a depth of peat as that up there. I was expecting it to be a lot shallower, but in terms of that particular type of coring gear, I've been down to about 12 or 13 meters with that kit. It becomes very, very difficult work. So obviously for each one of those extension rods that you add on top of the previous one, you're adding weight to the coring equipment. Of course, what you can do when you're pulling that out of the, because it's all manual labor, this to extrude that core, what you can do is you can attach and detach those rods as they sort of go in and come out, which does help to some extent, because obviously it's unmanageable when it's meters and meters long. But yeah, it's
You must have gone back quite a few thousand years then, if you're going that deep.
Yes. So there are sequences that I've looked at that go right back to the start of the Holocene. So the Holocene is the current epoch of geological time that we live in, and essentially it's the time since the end of the last glacial period. And often lakes particularly contain a record of sediment that goes back through the full Holocene, and then actually may even go back into the late glacial period, the period after the retreat of the ice, but still when conditions were extremely cold. So there's a potential for any of these archives of environmental change, particularly the lake sediment records in the British Isles and Northwest Europe more generally, to go back about 14,000 years. Now, of course, the depth of those sediments that are associated with that do vary according to various factors related to how rapidly sediment is perhaps washing into those basins, or how productive, biologically productive those environments are in terms of building up sediment over time. But yeah, it can always surprise you, and it's one of the joys of the work is when you're first starting out, with this type of thing, you really don't know what you're going to be finding. It could be deep, it could be shallow. You don't know what the sediment record is going to contain. So I had one instance, for example, where I started work on a little lake site down in Dungeness, which is in Kent, a little pits within the sort of the gravels there, and we actually found evidence for hemp retting actually having gone on during the medieval period. So it's full of pollen of Cannabis sativa, the hemp that was used to make rope and sails and things. So often, yeah, it's really exciting when you first get your material and you don't really know what you're going to find, and it's, you know, those first discoveries really nice.
Cool. Okay, we've got a question from Susan, who wants to know if the changes over time in the makeup of vegetation is due to changes in climate.
Yes, almost certainly, and definitely during, so just going back to this point that I made about the retreat of the ice sheet and the early Holocene. So certainly in that period of time during the present interglacial period, as conditions were warming up, and we were still in the Mesolithic in terms of people's activities. So the population densities were very low, and people were undertaking activities that generally have minimal impact on trees and landscape, like hunting, fishing, and gathering. In those situations, maybe somewhere between about 6,000 and, well, certainly within the Holocene, 6,000 and about 11,500 years ago, vegetation change was primarily driven by climate, but it was also driven by the ecological traits of those plants themselves. So what happened at the end of the last ice age, as the ice retreated, it left open landscapes that plants re-invaded to take advantage of that space and improve temperatures. So essentially there was a race on to recolonize landscapes and for vegetation to essentially exploit areas that had been essentially scraped clean by the advance of the ice and then left bare as it retreats. So definitely, but really the main driver of vegetation change in the last, say, 5,500 years has been people. So through sort of the introduction of agriculture, and then obviously later industry, and as population grew and pressure for different resources increased, that really took over then from climate as the primary driver of vegetation change. Although in some areas that are still relatively untouched by people, particularly upland areas, you can still see the effects of climate influencing vegetation change. So things like, for example, I showed you a nice picture of a really wet peat bog to start with. These types of environments are really responsive to climate change, so that you get, you know, changes in the vegetation on those surfaces responding to, you know, is it wetter, is it drier, is it warmer, is it colder, those types of things. So it's really a combination of factors, and as the pollen analyst, you have to try and ease out those drivers of vegetation change from you know, the evidence that you're presented with. But good question, Susan. And this is that's one of the things that I often, when I set questions for my students, I often ask them things like that. So brilliant question there.
Well done, Susan. So Sandra's put a question in the Q&A box asking, is there a historical pollen map for Aberdeenshire?
Not for Aberdeenshire. What there are that there are some academic papers and academic textbooks that, and they're a little bit dated now, that essentially map pollen percentages over the British Isles, and they show you how these have changed over time. I mean, what I could do is I could pass on some information about that, but there's no real sort of online map or anything, I'm afraid, that would show you that. What there is essentially, like I said, several journal articles that actually show the spreading of trees in relation to pollen abundances at different times in the landscape. And it's one of the main means that we actually are able to look at, for instance, how trees move back into the British Isles at the end of the last ice age, what directions they moved in and how fast they travelled, and essentially maybe other limiting factors like the climate, particularly as you get further north, how maybe reduced temperatures sort of slowed those advances. But yeah, unfortunately, no real sort of accessible maps. I mean, maybe this is, you know, something that the pollen community needs to think about.
I think we've got a hand up.
Yeah.
Christine's got a hand up, so I'll let her ask her question.
Okay, great.
You have to unmute yourself, I think.
Oh, yeah, actually, it's my husband that wants to answer the question, Harry.
Oh, hello, Barry.
Hi,
how are you doing?
Good. From Bennachie.
Yeah.
I just wondered, I know certain seeds can last for hundreds of years in the ground. I wondered how viable pollen can be when it's been hidden under the ground for several years.
Well, I mean, in terms of the viability for its intended purpose, you know, of you know, that pollen then reaching a flower and fertilizing that more or less zero, but these objects themselves, essentially that exterior coat that's made of a really sort of tough organic compound that is known as sporopollenin, that can last almost indefinitely within, if the preservation conditions within that setting are correct, which I mentioned. The two critical things here are the extent to which air is kept out of the pore spaces within that sediment column. So if it's really waterlogged, that's what you're looking for. This is what makes peat bogs and lakes brilliant, because they're typically, the water table's very high and it keeps that oxygen out that slows the decay. And also the other thing, if those settings are slightly acid as well, it really helps those objects be preserved for long time periods. So people have done pollen analysis on organic sediments that go back hundreds of thousands of years. So there's, for instance, there's an organic layer down in Norfolk known as the Cromer forest bed that's got pollen in there, and that's something like 500-600,000 years old. So given the right conditions, these things essentially can last indefinitely, and of course over much longer periods of time they can eventually become preserved within the geological record, as in, you know, they're essentially, when those sediments are buried sufficiently, compressed and turn into hard rock, they're contained within that. And I have colleagues within geosciences at Aberdeen who are more interested in those types of fossil pollen and spores, which are obviously millions of years old. So we have people here who are really interested at looking at pollen and spores at the sort of geological boundaries, you know, tens of millions of years ago. So yeah, they do have, there's a long sort of history of these objects in the ground.
Brilliant.
Okay, I think that's all the questions for just now. The lady who put in about the Mither tap being not the highest point, it says Oxen
right?
Craig's
Okay.
528 and Mither
Okay.
Tap's 518.
Okay.
But great lecture anyway. So yeah,
Yeah.
I don't know if you want to double check that or not. But
I will do. I'll check it later.
Take your word for it.
Thanks for pointing it out. Yeah, take your word for it.
Yeah, I'm not. I think that's all the questions. Susan, I think, did ask a supplementary question about the pollen map and saying, is there plans for one anytime soon? But I think you already kind of sort of answered that.
Yeah, not really. We're a dying breed, pollinologists. There's not that many of us left, but we are trying to train new people. But I mean, it's pretty specialised, and so, you know, these tasks related to essentially often databasing or presenting information, there's not many of us to do that, unfortunately.
Yeah, that's a shame. Well, I think that's us done then. we'll wind up there, but thanks everybody for watching, and please remember that all our presentations, if we've recorded them, will be on YouTube very shortly. So remember to subscribe and tick the button that says that you're watching our videos, and remember that our festival is going on to the 1st of December. So thank you very much, Ed, that was really interesting, and good evening to everybody, and I hope you enjoy your evening.
Yeah, thanks
Thank you.
folks.
Thank you. Bye.
Bye.